Hi guys, welcome to the next lesson on Learn Electronics for everyone. Yeah, for beginners, for people with more experience, this is for everyone. So in this video, we're going to talk about resistors in series and parallel. If you've watched the earlier videos, you'll know that resistors are effectively components that conduct electricity, current. Yeah, they conduct current, but they have varying amounts of resistance to the current flow. So the higher the resistance, the less current flows. Now with these resistors, we can make some very simple circuits. Resistors in series, as I mentioned, and in parallel. So what do these mean? Well, resistors wired in series are connected like this, and this is the symbol for a resistor. I'll just mention, by the way, probably depending on where you live, you may actually use this symbol for a resistor. It doesn't matter, use whichever one you prefer, they're both recognised as being the same thing. So here we have two resistors, and they're connected in series. That means one end of one resistor is connected to the end of the other one, okay? And then let's put three resistors in series, like so. So we now have three resistors connected in series. How would you do this in practice? Well, we have some resistors here, so let's connect them. Each of these resistors, by the way, has a marking on it. Okay, you see those coloured stripes there. These are actually 1000 ohm or 1 kilo ohm resistors. Now, I made a video a few days ago, all you need to know about resistor markings to fix stuff. That was originally meant to be part of this series, but I realised it had more of the universal appeal. So if you want to know how these markings work, and you do want to know for sure, go and watch that video and you'll understand all the different ways of marking a resistor. But for now, let's assume you have watched that video and you will know that brown is 1, black is 0, and the red is 2 more zeros, so that's 1000 or 1000 or 1 kilo ohm, and the gold one is the tolerance. If you didn't watch it, well, you know now why you should go and watch it. So let's connect our resistors in series. There's a lot of tutorials on this topic, and by the way, they all use far too much mathematics. We're not going to do that here, but we're still going to understand what we need to know. And most of these use what's called a breadboard, where you can plug these resistors in and you can play around, you can experiment. And I'm going to do the same thing. You can see my breadboard, and I'll just explain this in a moment. Had something of an accident. That was on a live broadcast we made a few weeks ago when something set on fire, okay, and that's what caused that. But let's not worry about that too much. I have ordered a new one. So what's this breadboard thing? Well, you can see it's a matrix of holes, effectively, with gaps, okay. That's a bit of fluff, by the way, which came from the thing that exploded and set on fire. Okay, we have some more sets of holes up here. You can see we have red lines and black lines. You can use these in many ways, but the idea with these things is you take a component and you plug it in to the holes any way you wish. Okay, you just insert it into the holes, and this is just a quick way of putting circuits together to save you soldering, but yeah, we could solder them. So this is breadboard. I'll just show you how these holes are connected to each other. So basically each row of 6 are all connected together, okay? So there's a connection between all these 6, then there's a break, then there's a connection between those, and the same with all the other ones, and then each row again. So each row is isolated from each other, but they're all connected together. Probably easier if I draw it on a bit of paper, it usually is easier. So in this breadboard, what we have is, we have a row of 6 holes. These are the holes with a piece of metal. In fact, you can see where I burnt it. I'll show you in a minute. We have a gap, and then we have the same thing. And then we have another one, the next row, 6 holes, and so on. Yeah, that's what we have, and so on. Under the holes are little metal springy clips, which are easily visible on this because you can see what's happened to it. Yeah, so I'm sure you can see that in there is a row of 6 metal springy clips. You can see them here. Yeah, rather distorted. So that's what effectively connects the row together. When we push our component into the hole, it just connects into the springy clip. Okay, so that's what the breadboard is. If you're wondering about the red and black stripes, well, usually the red is used for power, and in fact on this one all these 6 and these 6 connect together, so we've got a row of 12, hence the red line, a gap, another row of 12, and the black line is where we connect the negative. This is usually the positive, and on this one all the rows on the negative are all connected together. That's why there's a solid line, and the same at the other end. On this one then, and these come in different sizes and different styles, this has vertical strips, so 1A to 1F are all connected together, 2A to 2F all together, but they're not connected to each other horizontally. So that's how it's laid out. I do suggest you buy one of these. If you're learning electronics, it's a very useful thing to have. Okay, so that was a little sidetrack. Let's get on with these resistors. And let's connect some of them in series. So there we have 2 resistors in series. What's the total resistance? Each one is 1000. Well, let's measure it. So this is a multimeter. I'll talk about multimeters very soon. Probably actually in the next episode or 2, I think. It's a good time. So the multimeter can measure various things. We'll talk about it soon, but I've set it to measure ohms. So this will measure the resistance of the resistor, or the 2 in series. So what do we have? Well, that's reading 0.986 kilo ohms, or 986 ohms. Resistors are made within a tolerance. These are 5%, so that's within tolerance. They're never going to be exact. And we can measure, obviously these 2 are connected together. I told you this whole strip is connected together. 0 or close to 0. So these resistors, these 2 ends are connected together, and then the other one connects to here. And we have 0.988 ohms. It's close to 1000. So let's put this on our diagram. So this one, close enough, is 1000. 1K. 1 kilo ohm. And this one is 1000. Okay. What's the total if I measure across the 2 resistors? What's the total if I measure across the 2 resistors? Well, let's do it. Here's our 2 resistors. What do they measure from end to end? Well, they measure 1973, so basically 2000. So the total from one end to the other, there to here, okay, is 2000. 2K. What do you think will happen if I add a third one, the same as we did before? Okay, well, let's use a different value. So this resistor, different coloured stripes, you can see orange, green, brown. This is a 390 ohm resistor. Let's put it into our circuit. So from the end of this one, I could go into any of this row. It doesn't matter, they're all the same. Stick it into that one, why not? And into another row, any row, it doesn't matter, any hole. Stick it in there, okay? So what we have now, well, this resistor, and I can measure from here or there because it's connected to each other. That strip, yeah, to here. I said it was a 390 ohm resistor, and it reached 391. Okay, what's the total? 2,364. Basically 2,390, because what's happened is this one, 390R or 390 ohms, is just added to the other two. So we now have 2,000 to there, and from here to the other end, okay, we have 2,390. And I'm sure you can see, if I measure from here to here, this point, we should be able to work out what we're going to see. We're going to see 1,000 plus the 390 in series. So we can calculate now, just by playing with this, that if we go from here to here, we're going to see 1,390. Okay, but let's prove it. So if we measure from here to here, yeah, 1,379. So adding resistors in series is very simple to calculate. You just add them all together. So the formula, let's have a formula. Resistance total, the total resistance equals, let's call this R1, R2, R3. We could call them anything we wanted, but why not call them R1, 2 and 3? So the resistance total equals R1 plus R2 plus R3 plus however many more you have. Yeah, add them together. And we've proved that, so we can say that is a very simple formula with resistance series, just add the values together. How about resistors in parallel? And what does that mean? Well, connecting resistors in parallel means we connect the resistors across each other. So we have one resistor, the other resistor, and they're connected this end to this end, this end to this end. So what do you think the formula is here? Well, let's have a look. So we'll take a 1,000 ohm or 1K, whichever you want to call it. I'm going to start calling them K because it's easier to write than 1,000, and we'll take a 1K. If we measure from here to here, what resistance do you think we'll see? Well, let's have a look. So first we need to wire this up, and as we said, we need to connect the resistors across each other. So this end to this end, and doesn't really matter where we stick it as long as it's on the same row. In fact, I'll deliberately stick it in another row just to prove the point. This end to this end. Okay, so they're now in parallel. What do you think they'll read? Well, let's have a look. Okay. $494. So basically 500. So it reads half of the original value. The resistance is now half. So if we take 1,000 and 1,000 and we put them in parallel, we end up with 500. What do you think will happen if I put another 1,000 in there? Well, I think, let's talk about it before we actually do it. I think we can all probably agree that if two of them in parallel gives us 500, then three of them in parallel will give a third. 500 is half of that, so three in parallel will give a third, 333, yeah? Let's try it. There, you can see we have three of them. So I think and I hope you're all following with this. This is going to be like 333 unless we are really, really wrong with what's happening. Let's have a look. Yeah, 329 given the tolerance of the thing. So if we connect 3 in parallel, $333. And I'm sure you can imagine that if we connected 4 in parallel, we'd get a quarter or 250. So when the values of the resistors equal each other, it's easy to understand what the result is going to be, but it's not easy to see quite what the mathematics is. How would you express that as a formula? And what would happen if we take 2 completely different value resistors? Or even 3. Yeah, let's use 3. So we now have a 1000, a 1000, and this is one of our 390s. Okay, 390. So you can see they're all in parallel with each other. What's the value going to be? Well, one thousand, 390. Well, I'll tell you what the value is going to be. It's going to be not very easy to work out. Yeah, you can see that's not going to be easy to just say, okay, well, that and that 2 in parallel should give us 500, half, and then you got 500 and 390. So what's that? Does it even work that way? So there is, in fact, a formula for working this out. Now, I am going to show you the formula. I'm going to show you the formula because I had to learn this back in the day. But fortunately, you guys don't have to learn it because it's a very easy way. And the formula is resistance total, the total resistance equals 1 divided by 1 1 divided by 1 divided by the value of R1 plus 1 divided by the value of R2 plus 1 divided by the value of R3 plus however many more you have. And that's why you don't want to be doing the maths. Yeah, it's horrible. I had to learn this in the early 1980s, and that's because we didn't have things like the internet then, but we had calculators. So I had one of these scientific calculators that you could actually enter formulas, and I entered into my calculator the formula for this, and I made 2 or 3 or maybe 4 formulas. One was with 2 resistors in parallel, one was with 3, one was with 4. And when we went into the exams, you could take a calculator with you, yeah. And of course, with mine, I just went formula, parallel resistor. Then it'd say enter R1. I'd put R1 in, enter R2. I'd put it in. I'd enter R3. And I'd put it in, and it would tell me the answer. Yeah, much quicker than this. On to the next question. Was that cheating? No, that's just using your head and thinking about it a bit. Yeah. So if I didn't want to work this out in the early 80s, I'm sure you don't want to now. But we're going to do it once. Just once to prove it. And then we're going to measure our circuit to see if it's right. And after we've done that, and if it is, then I'll show you the other way. You'll never have to do this again. And you won't need the scientific calculator either. Okay, so what do we have? Well, we have R total. That's what you want to work out. Yeah. Equals 1 divided by 1 over 1000, yeah, plus 1 over 1000 plus 1 over 390. Okay, so let's work it out. And we'll break this into chunks, it's easier. So the first thing we're going to work out is 1 over 1000, 1 divided by 1000. What is that equal to? Well, 1 divided by 1000 is 0.001. Okay, so we have that. So that is 0.001. And although I could calculate it again, I think it was Einstein who said that madness is performing the same experiment over and over again, expecting a different result. Yeah. So to avoid madness, if we do it again, it's going to be 0.001. Yeah. We can all agree on that. So what's 1 over 390? Well, 1 divided by 390 is 0.0025, that thing. Yeah, it's that thing. So it's a very long number. Something like 0.0025 blah blah blah. Okay, it's that. Now we need to add now 0.001 to 0.001 to that. So let's just add 0.002 because that's the sum of these. Yeah, you like a bit of mental arithmetic. So let's add 0.002 to that long number. So that long number plus 0.002 is another very long number, 0.00456. So this plus this plus this is 0.00456 blah blah blah. So to complete the formula, we've now got to divide 1 by 0.00456. Yeah? You see why this is horrible? Do you wonder how scientists ever invented anything? Yeah? Back in the Victorian times when they didn't have calculators? Well, use the head, yeah? So, or maybe we're just lazy. Probably not. Comments. So, I'm even going to be lazy still. I'm not going to type this number back in again. I'm just going to divide 1 by that. So I'm going to put that number in the memory. And then I'm going to put 1 divided by whatever was in the memory. That equals. And I come up with an answer, which is 219 ohms. Let's measure our resistors and see if that's correct. Okay, so we're expecting 219. Give or take the tolerance, we know about that. So what have we got? 217.5. So we know the formula is correct. We also know it's an absolute pain in the ass to work it out. So this is where you guys get to benefit from modern technology, which I didn't have the benefit of, by the way. Google resistors. I spelt it wrong, but he still found it. Resistors in parallel. Okay, and we have calculators. Look. So let's try the calculator. How many resistors do we have? 3. Okay. Value the first one, 1000 ohms. Value the second one, 1000 ohms. Value of the third one, 390 ohms. Okay, calculate the answer, 219. So we know the maths was perfectly correct, and we know this is why we don't want to be messing around dividing 1 by all sorts of things and adding them together. Okay. So that's all well and good, but why do we want to be bothering connecting resistors in series and parallel, apart from learning electronics? Yeah? Why do we want to do this? Well, there's a few reasons why we might want to do this. One reason may be if you don't have the correct value resistor, or the value you want is not manufactured because you don't get resistors in all values you may want. So you can use 2 or more resistors in series, in parallel, or even in a combination of both. something like that. 2 in series with 2 in parallel in the middle. You can do these things. Okay. If you want to work this out, by the way, you calculate what those two come to first, and then you go to the equivalent of 3 in series, and you work out the total. Yeah. Or you find some other resistor calculator that'll do that for you. So you may want to do it because you want to make a particular value resistor. You may also want to do it if you have a circuit that is passing more current than your resistor can handle. You saw in the first video we had the resistor set on fire because it couldn't handle the wattage dissipation. So what you can do with resistors in parallel is you can connect them like so. We'll draw it this way up. Okay, let's have 4 of them. We can have as many as we want. Running out of space here, but it's almost done this lesson. We can do something like this, plus minus, and we could, for example, have each one of these resistors is a 5 watt resistor. Okay, 5 watt, 5 watt, 5 watt, all of them. And then when the current passes through, each resistor will carry approximately, because they're not always exactly the same value, but very close approximation of the same current. So if there was 4 amps flowing through here, 1 amp will go through this one, and 1 amp will go through this one, and 1 through this one, and 1 through this one. And now each resistor has a quarter of the current, so it will dissipate a quarter of the power. So it's sharing the load. So that's a common reason why you would want to put resistors in parallel. Why would you want to put resistors in series other than making up a certain value or just to learn electronics? Well, when you connect resistors in series, like so, and you apply a voltage, plus or minus, what voltage do you think you'll get in the middle? Yeah, so if, for example, we put our black meter probe on here, there's our multimeter. I always draw analog ones, don't ask me why. And we put our meter here, and say this is a 12 volt battery. Well, we're going to see 12 volts, yeah, but what happens if we put the meter lead here? What are we going to see? Well, that's the topic of the next video, because this circuit is one of the basic building blocks of all electronic circuits, and it's called a potential divider. Okay, if that's got your interest, we'll talk about them soon. Next lesson. Ciao for now, guys.